Hello and welcome everyone to today's webinar, and the topic is smart home device design and Wi-Fi connectivity using electromagnetic simulation. And my name is Naveen and I'm an application engineer at Remcom, supporting our full wave simulation products. And with me I have Sam Magliaro, who is an application engineer as well, and he supports our ray tracing tools. And for today's presentation, we'll be looking into how we can optimize a tri-band antenna array in our full wave solver XFdtd and perform a throughput analysis in our ray tracing tool Wireless InSite. So to start off, I would like to give you the overview of today's presentation. So first, I will be covering the Remcom's product lineup, and from there, give you a peek into the smart home scenario that we'll be looking into and simulating in both XF and Wireless InSite. And following that, we'll be looking into a tri-band access point simulation in XFdtd using our array optimization feature. And after that, we'll be exporting the antenna pattern along with its codebook, the different phasing for antenna arrays into Wireless InSite, and a stop at a camera, the user device which we'll be using in the smart home scenario. And after that, I will be passing on to Sam, who would be showing you how to set up a MIMO access point and camera in a smart home environment and perform throughput assessment using different MIMO techniques that are available in Wireless InSite. And throughout the presentation, we have the GoToWebinar window where you can undock the questions area and can type any questions you may have. We have moderators today, Tarun Chawla, Jeff Barney, and Greg Skidmore, who would be answering the questions throughout the presentation. And in the end, if there are more questions or any questions unanswered, we'll have a 10 to 15 minutes Q&A session where we'll be taking the questions. So our product lineup. So XFdtd is our full-featured EM solver, which includes a full wave static or biothermal optimization and circuit solver kind of tools to tackle applications like antenna design and placement. We also can perform biomedical simulations, the specific absorption rate simulations, and also EMI and EMC analysis using our full wave solver. And the second tool, the Wayfarer, is a high fidelity radar simulator which can account for multipath from structures and vehicles in the immediate environment of a radar system. And applications might include simulation of automotive drive scenarios or even perform RCS calculations. And this is one of our ray tracing tool as well. And for today's presentation, we would not be covering Wayfarer. The tool that would be of interest is Wireless InSite. It's again a suite of ray tracing models and high fidelity EM solvers for analysis of site-specific radio wave propagation and wireless communication systems. So InSite more of provides RF engineers with a tool to design wireless links, optimize antenna coverage, and access key channel and signal characteristics for different RF and millimeter wave applications. So the smart home concept as such includes establishing reliable links between various devices internally, or which can be including speakers, thermostats, doorbells, and cameras in the house. And in this presentation, we would be first looking into how to design two products, user devices, the first being the wireless access point, and then a camera. In the overall scenario here, we have three cameras which are placed, one here and one at the back of the house and one in this location. And we have two access points, one placed here and the other one in this location. So first I'll walk you through how we can perform the analysis of the antenna arrays used in the user devices, and then pass on to Sam, who would be more walking you through how to perform or analyze the reliability of links and showcase SNR and throughput of these devices. So the access point, it's designed to operate in the three different bands and three different frequency ranges: 2.4, 5.2, and 6 gigahertz bands, covering and supporting most of the Wi-Fi standards, including Wi-Fi 6E. And this access point contains two big dipole elements, planar dipoles here marked in red, that are operating in 2.4 and 6 gigahertz bands, and the four smaller planar dipoles are resonating at 5 gigahertz. And the S parameters for these antennas are plotted in the right. So the red one covering the 2.4 and 6 gigahertz bands for the larger one, and the blue one more of representing the S parameter of one of the smaller element excited. And in the bottom we have the radiation patterns showing the gain of these antenna at three different frequencies: the 2.4 gigahertz with the arrow denoting the peak gain region, peak gain direction, and here the 5.2 gigahertz, and so forth, the 6 gigahertz element. And with multiple elements here, we can configure them as arrays and perform beamforming to effectively cover a wider area. And to perform such analysis and on these devices, we can use a feature called array optimization within XF, which requires users to specify the directions in which they want the maximum power to be focused, and the algorithm automatically finds out the appropriate phasing for the different antennas that are forming up the array. So in this case, I am combining four smaller antenna elements here, the 5 gigahertz ones, to support 12 beams in the azimuth plane, and the larger elements supporting the 2.4 and 6 gigahertz, which are combined, and beamforming is performed on them. And here in the bottom, we have a max hold pattern, which is plotted for these different beam combinations. Max hold being a combination or an envelope of all the different beams which are covered by that particular element for that particular array. And to the right, we have a cumulative distribution function plotted for these max hold patterns. And this gives us a measure of knowing how well or how many different angles the array is capable of covering. So in this case, let's take the example of the black curve, which is a 5.2 gigahertz array, which shows that we have a cumulative distribution function of cumulative probability of 0.18 for input power of 30 dB milliwatts, which tells us that for about 82% of the angles, the antenna has a positive gain. And next, I would like to demonstrate the same on performance analysis in the tool. So here we have the same speaker, which I've imported into XF with the four smaller dipoles at the center and the two larger dipoles in the corner. And we have a translucent case that is covering the speaker, and we have a speaker cone which is also placed to include in the electromagnetic modeling of these structures. And each of these arrays are excited through lumped components, and I have set up a far zone sensor to extract the radiation pattern for these different arrays. And I have already performed FDTD simulation on this, and I would like to first show you the radiation patterns for the same. So first we have the gain for the 5.2 gigahertz, element, and here is the gain of the 2.4 gigahertz element, and moving on to the last, the 6 gigahertz radiation pattern for the larger dipole. And to perform or to understand how well we can create antenna arrays out of this, I would like to show you how to perform array optimization in this case. So that is something we can access through create simulations, and under array optimization, I select the simulation with the FDTD results, and then proceed to define the different individual antennas that form up my array. And in this case, I'm combining the two 2.4 gigahertz elements into one and providing a total of 1 watt power, and sending in a set of phases which our algorithm uses to find out the maximum or the phasing for combinations that provides a maximum gain in the specified directions. And the next would be to define the analysis definition, where we are giving in the directions to the algorithm in which we want the uh, beam to be pointing at. And in this case, considering the Wi-Fi application, we want most of the horizontal plane covered. So I'm setting my theta to around 90 degrees and stepping my phi angles from 0 to 330 in steps of 30 degrees, resulting in 12 beams for the this array. And similarly, we perform a similar definition for the 5 gigahertz array too. And with the definitions completed, I can create and queue the optimization. And this takes a few seconds to run the simulation. And just to save us some time, I have already performed an array optimization here, and I would like to show you the results from that simulation. So if I go to the results, I would like to first plot the max hold patterns for these two arrays. So I will just set up the opacity to a little lower so that you can see how it is with respect to the speaker. So this is how the max hold pattern looks for the 5 gigahertz, covering most of the horizontal plane and some of the directions on the top of the speaker. And similarly, this is how the max hold pattern looks for the 2.4 gigahertz and so forth for the 6 gigahertz, giving you the combination of the overall beams combined. And to plot the cumulative distribution function, I would select the gain or effective isotropic radiated power and select the create CDF plot, which then creates a CDF plot, which is as shown in the slides. So coming back to the presentation, the next step from here would be to transit the UAN files, which contains the radiation characteristics of the array, and also move in the codebook into Wireless InSite, which Sam would be utilizing in Wireless InSite to perform propagation analysis. And to do this, I will get back to the project here and quickly show you how we can export the gain details into Wireless InSite. So under results, we have the options to export as Wireless InSite array, which would take out the radiation patterns for individual elements, and so on. We can have a custom script which is written to extract the codebook information as well, which would then pass the different phasing details to Wireless InSite. And the next part, the user device, which would be used in the smart home scenario, utilizes two conformal antennas, which are wrapped around the interior surface of the camera, and these are designed to connect to the tri-band Wi-Fi system here. In the right, you can see the S parameters for one of these antenna excited here at the center. So this is the peak. This is the dip at the 2.4 gigahertz, 5 and 6 gigahertz. And similarly, we have the radiation patterns at these different frequencies. And you can see at the 2.4 gigahertz, we have a much wider area being covered by this antenna. And with 5.2 gigahertz, this covers more of much narrower region. And 6 gigahertz provides more of a uniform coverage and also some coverage on top of the camera. And as per the array performance, we are using array optimization here as well. And the different directions that we provided utilize two elements together to form an array. And we are generating 144 beams in elevation plane. And this is how the max hold patterns for these three different frequencies look like. And so forth, plotting cumulative distribution function for these three frequencies would yield the plot on the right. So the steps are very similar to what we performed for the smart speaker. So I will not be getting into this project again. So now I would like to pass the control to Sam, who would be importing these arrays and walking you through the different features Wireless InSite has for performing propagation analysis on this user device in the indoor environment. Okay. Okay.
Hello, everyone. As Naveen had mentioned earlier, I'm Sam Magliero. I'm another application engineer here at Remcom, focused mostly on our propagation ray tracing side of the tools we have here. So I'll be going over the Wireless InSite portion of this demo. And just as a high-level overview of what I'll be going over, we're going to be looking at some of Wireless InSite's capabilities for MIMO processing, as well as the process that we use to transfer the information at the antenna patterns and the precoding tables from the XF simulations that Naveen had shown us, how we can get those into InSite for propagation analysis. And then we'll be taking a look at a brief live demo of the actual smart home scenario we've put together to give us SNR and throughput outputs. So starting off, we have our Wireless InSite MIMO Techniques. These are all of the built-in MIMO techniques that the tool has available. So we support several different things, several different methods focused mostly on different approaches to beamforming, diversity combining, and spatial multiplexing. So the way this works is that this is actually done as a post-processing step that acts on the output that we get from the main simulation, and we can use that to then determine the final signal to interference plus noise ratio for throughput and BER calculations. So here at the bottom, we have kind of a workflow of how all of these how the whole simulation comes together and how we get to our final output. So we start with our scenario inputs. These are things like the geometry in the scene, the terrain, the buildings, as well as our actual MIMO array, our antenna patterns that we'll be importing from XF and so forth. We run the main simulation in Wireless InSite to do the ray tracing, which yields our main simulation outputs, things such as received power, complex impulse response, and in this case, most importantly, the H matrix. So that is where we get into our communication system analysis. This is the post-processing step where it looks at the output that we got from the main simulation, applies these different MIMO processing methods, and then that yields us a final SINR throughput and BER bit error rate metrics. So moving on, we have our complex channel matrix, or the H matrix. And so what this is actually just a matrix of the signal between every transmitting and receiving element within MIMO arrays on either side of the channel. So here we're looking at R is the received signal here, and S is the transmitted signal, where H is our channel matrix entry. And then on the right here, we can see an example of a 2x2 channel matrix for MIMO, where on the left we have our transmitting elements, on the right we have our receiving elements, and we can see that we're actually calculating all of the different channel combinations between these elements. From there, we have our different MIMO techniques for receiver diversity combining. So the goal of this is to combine the signals from all of these different subchannels and all of our different antennas into a single, more improved, more optimized signal. So we have three built-in methods of doing this, starting with selection combining as the most straightforward approach, where we're just choosing the signal with the highest SINR of the available channels in the H matrix. Equal gain combining will actually do a phase alignment and then sum all of these channels to get a stronger combined signal. And then maximum ratio combining does this same phase alignment, but then also adjusts the actual magnitudes to optimize the final summed signal that we get. So here on the right, we have diagrams of sort of what's going on for each of these methods, where for selection combining, we're just choosing the best of the available subchannel signals. Equal gain combining, we're applying this phase shift and then summing all of the channels together. And then maximum ratio combining, we have the phase shift as well as the adjustment to magnitude before we sum to get an optimized final signal. Moving into our other beamforming methods, we are starting with maximum ratio transmission, or MRT. And what this does is it actually uses the channel matrix to form a fully ideal beam between the access point and a user equipment. So this mimics the way that behaves in the real world, where the access point and the user equipment will estimate the channel state information through measurements and then use that to create a steering matrix for the beam. And in the case of MRT, what this results in is actually an idealized case where we have a strongest possible beam to all of the devices in the scene. So on the right here, we have some simple examples of this type of beamforming, where it could be something like home Wi-Fi to a user device, or something like a massive MIMO array using millimeter wave transmitting to multiple devices. Alternatively to MRT, we also have the opportunity to beamform with the precoding tables. So these are the tables that had been exported from the XF simulations that Naveen had gone over earlier. So these are actually a table of complex weights for all of the elements in the antenna. And then during the calculation using this precoding table, the model will choose the best beam to each individual receiver location in the scene. So on this slide, we have a simple example of sort of how this works and how the precoding tables can compare to the maximum ratio transmission. So in this example, we have 10-degree beams in this table. Within the table, it's a total of 78 beams that cover plus or minus 60 degrees in the horizontal field of view and 50 degrees in the vertical with 10-degree spacing. And then again, we're comparing it to the MRT here. So these two images at the bottom show the different weights for different beams that are within these precoding tables. So in this case here on the left, we just have our 0-degree beam, and we can see the maximum energy is being focused directly directly outward along bore site of the array. Whereas when we use the 60-degree beam in the table, we can see that the actual the main signal is being emitted from the side here and steered using that beam. And then up here in the graph, we have a comparison of all of these, where the blue line is the 60-degree beam that we can see here. The red line is the 0-degree beam, which we can see aligned directly in the middle of the main bore site. And then green is a combination of all of these beams to give us a closest match that we can get to the actual MRT, which is in orange. So you can see that these two approaches are comparing quite closely, particularly in the main path of the array. Lastly, we do also provide closed loop spatial multiplexing, and this is using singular value decomposition. So this actually determines the weighting matrices for the transmitter and receiver with the goal of creating orthogonal streams. And so what this allows us to do is kind of identify exclusive subchannels between elements of these arrays and therefore increasing the overall throughput. So we can see here on the left, we have what the actual channel matrix traditionally looks like, where we have all of the subchannels cross-talking to all of the other receiving channels. And then after applying these weights, we can see that we have these isolated streams between independent transmitter and receiver element pairs that can give us that throughput increase. When it comes to actually loading the MIMO data from the XF projects into Wireless InSite, we're able to do this directly in the tool for the antenna patterns and the actual entire array setup itself. So the position and orientation of all of the elements within the array, as well as the gain patterns that are applied to each array. And that, of course, is the benefit of that is that this process is much faster and easier to get these complex arrays set up, particularly if you start getting into large MIMO arrays with many different patterns and many elements to define. So we can see here, we have a diagram of this sort of workflow where we can import the XF MIMO antenna, which will look something like this, in this case for a 4-element antenna. We can then assign these antennas to actual transmitter and receiver locations in the scene, like where we want the access points and the cameras to be. And then during our communication system, the post-processing step after the simulation, that's where we can apply our precoding table that we exported from XF and use that for the actual beamforming that happens. The smart home scenario itself is designed using access points. These are the smart speakers that we had looked at in the earlier XF project. So these smart speakers are access points. And we have one placed on each floor of the house, as well as 3 of the exterior smart cameras. We also have a look at general coverage on each floor, as well as SNR and throughput along a receiver route that goes up the flight of stairs in the back here. So we can take a look at the change from going to the first floor to the second floor in terms of how both of the access points are reaching that. So the access points themselves are operating on Wi-Fi 6, 6E, and they are tri-band access points. So those will operate at 2.4 gigahertz, 5.2 gigahertz, and roughly 6 gigahertz. At 20 or 80 megahertz respectively in bandwidth. And then the throughput is using the modulation and coding scheme for 802.11 AX. As for the cameras, those are dual band operating at 2.4 and 5.2 gigahertz. For the geometry of the home, we have material properties assigned to different parts of it that will respond differently during the ray tracing. So each color that you can see here actually represents a different material, and these are all broken up by the different types of objects they are. We can see we have couches and beds, glass on a shower back here. These interior walls are drywall. All of the brown material is wood. And then currently in this image, we have all of the exterior walls and windows and the roof just hidden from view so we can see into the house. So now I'm going to shift over to Wireless InSite itself, looking at that tool to kind of walk through how we load in this data from XF and take a look at the actual scenario we have set up here. So firstly, I'll go ahead and just show how to import the actual array for MIMO antennas that have been exported from XF. So this is very easily in Wireless InSite. We can simply open our project menu and go to import, and we have an option for XF MIMO antenna specification. We can then navigate to where we had exported our patterns, and we'll see an index file that we can that defines all of the metadata about the patterns and where they're oriented. So we can choose to open that. And we can see here now that we've actually imported many different antennas operating at different frequencies here. If we were to open these, we can see that we actually have our different antenna patterns brought in, as well as positions and orientations for each of these. So just like that, we can bring in an entire MIMO array and have it pre-configured. If we move over to the full smart home scenario, we can see that there are two different antennas that we had loaded in here from XF. Here we have our smart speaker access point with our 4 elements and our 4 patterns assigned, as well as our dual band smart camera that we have mounted outside the house in several locations. So this instance of the project is looking at the 5.2 gigahertz band of both of these objects, both of these user equipments. We can see on the left side here the locations of our actual access points. We have the one located underneath the TV here on the bottom floor. There's the second access point is up here on a desk on the second floor. We have one smart camera outside overlooking the driveway. Camera number 2 is actually behind the house, mounted on the back side. And then camera 3 is on the front corner here by a balcony. We can also see here a better view of the receiver route that's going up the flight of stairs between the first and second floors. So we can take a look at that to see how the signal will change or improve based on access point 1 communicating with that receiver route, access point 2, and the combination of both. Moving over to our comm systems, this again is the post-processing step of the simulation where we are actually doing our MIMO beamforming. We have a few different ones set up in this project to compare the different methods. So here we have our precoding and beamforming table selected as our input method, and then we have our table defined that had been exported from XF with all of our precoding beams in there. And then for our receiver diversity combining, this particular communication system is using the selection combining. And then down here under throughput options for our wireless access method, we're using a user-defined table as opposed to one of our built-in options. And you can see that this one is defined, the user-defined table that we're using is for 802.11ax operating at 80 megahertz bandwidth. So the same is true for these other ones. The only difference is that we're changing the diversity combining approach. In this one, we're using max ratio combining. And then lastly, we're doing 2x2 MIMO using closed loop spatial multiplexing. So coming back to the slides, we can take a look at some of the output. So looking at the propagation paths, we can start there looking at the paths between access point 1 and access point 2 on the second floor. That's here on the left. This is just to get an idea of the multipath that's going on in the project to see sort of how it's propagating between these 2 points. So we can see a lot of these paths actually going through the floor directly up to the second access point. On the right here, we're looking at access point 1 transmitting to camera 1, which is overlooking the driveway outside. And it's a little bit hard to see here on the slide, but you can see that there are a lot of the propagation paths are actually coming through a small window on the door of the house. So they're transmitting directly through the glass and getting pretty good coverage to the camera out here. Next, we can look at the total coverage for both floors that we're looking at for signal to noise ratio. On the left here, we're just looking at access point 1 and its coverage to both of the floors. And then on the right, we introduce the second access point, and we're looking at the total combined signal coverage to both floors while both access points are active. And this is while ignoring interference between the two. So here we're looking at the SNR and throughput to the cameras from both of the access points. So on the left here, we're looking at the SNR, and we can see that some of our points have lower performing SNR than others. Those in particular would be the dark blue and the light blue points, which are actually access points 1 and 2, both transmitting to the second camera, which was the one behind the house, which is actually outside of line of sight for either of the access points. And you can see here when we're actually looking at the throughput to both of those, to that camera from both of the access points, the throughput we're getting is negligible because of how blocked it is. Here we're looking again at SNR and throughput, but this time we're looking at it for the receiver route that's going up the stairs from the first floor to the second floor. So again, we have SNR on the left and throughput on the right. The red and blue lines respectively are independent measurements for the each individual access point to the entire route. And then the green is actually a combined best result from both of them. And we can see a similar trend here on the throughput where as it shifts floors, the higher performing access point will change. So when we look at the total of that being the green line, we can see pretty good performance up the entire route because of both access points. Now we can take a look at comparing some of the actual MIMO techniques that we had set up in our communication system. So on the left, we're looking at throughput from access point 1 to the stair route. And on the right, we're looking at the same throughput to that stair route, but from access point 2. Red and blue, the blue line is maximum ratio combining for the receiver diversity, and then the red is throughput from selection combining, while green is using the closed loop spatial multiplexing or the 2x2 MIMO. And if you'll remember, we had the orthogonal streams when using the spatial multiplexing, so we actually get quite a significant boost in the throughput when using that method. When comparing the different frequency bands, again, because these were tri-band access points, we can see the SINR here on the left side, excuse me. We have 2.4 gigahertz yielding the best SINR response, with 5.2 and 6 gigahertz being a little behind, performing similarly. But when we look at the actual throughput for that, we can see that the 2.4 gigahertz is now performing the lowest due to the bandwidth of that band. while 5.2 and 6 gigahertz are performing much better for overall throughput. Again, here we are comparing access point 1 at 2.4 gigahertz or 5.2 gigahertz. And this is looking at SNR on the first floor. So we can see that we are again getting better SNR at 2.4 gigahertz than at 5.2. But when we take a look at the actual throughput, we're seeing that 5.2 yields much better throughput than the 2.4 does. And of course, everyone is always welcome to reach out to us directly. Here's a slide with some of our contact information if you'd like to get a hold of us and ask any questions or have any other inquiries. But in the meantime, there's the questions box on the GoToWebinar window that you should be able to see, so you can ask any questions in there. I see a few had already come in that have been answered. Does it take a BIM file? I'm not immediately familiar with a BIM file format. So natively, I will say that it's not currently supported, but depending on the contents of the file and what you're trying to bring in from that, it could likely be converted in some capacity. If that's something you'd like to talk about, we can certainly explore that more. Not a lot of questions coming in, but we can give everyone a few minutes if anything comes up. Okay, it looks like we're not getting a lot of questions here, so we can go ahead and wrap up. Of course, if you do have questions that come to you later, please feel free to reach out to us at any time. And we can respond through email or set up a call to talk about that. But if there are no other questions, then I would just like to say thank you for your time. Thank you for attending. Thank you to Naveen for the other half of the presentation. Oh, we have one other question coming in here. How close are the measurements, how close are the simulations to the measurement in the same environment? So that would be looking at general validation that we have. That's a bit of a complex topic to cover here in any real depth. But we can reach out through email and provide some examples there and talk about how we have validated our simulation approaches here. Do we have many companies in England using these tools? That is something I would need to double check. We do have global distribution in many markets, so I'm inclined to say we do, but that is something I would, of course, want to double check and follow up on before I make any concrete claims. Okay, if there are no other questions, then we can go ahead and wrap up here. Thank you everyone for your time, and thank you for attending, and have a wonderful rest of your day.